Hey everyone. Welcome to the Machine Learning for Audio Study Group from Hugging Face. So this will be the first session. I'm Omar Sanseviero. We have Bibi here as well. Thank you very much, Bibi, for being here.
Hello.
Awesome. So we'll go over the logistics in a bit, but let's first introduce ourselves. So my name is Omar Sanseviero. I'm a machine learning engineer at Hugging Face. Previously, I was a software engineer at Google Assistant, and before that, I had a community which was focused in teaching machine learning in Spanish, which was called AI Learners. Very nice meeting you all.
Nice. Just a quick introduction about me. My name is Vaibhav, but you can call me VB. I am currently a master's student at the University of Stuttgart. I study computational linguistics, and I work with Deloitte Tax over here, and working on natural language processing plus speech synthesis use cases. I for the Before the pandemic started, I was working with Deloitte Consulting back in India on strategy and analytics, and have been actively researching for about a year now. Nice to meet you all.
Awesome, that's very cool. So just to give a bit of a super high level overview of how this study group is going to be organized, is that these first few weeks we'll kick it off with some of the most basic stuff. So if you don't have any idea about how machine learning is used for audio, these first three sessions will be perfect for you. After that, we'll focus a bit more on reading papers, reading resources, discussing things that we as a community decide. And then we can even invite people from the Hugging Face team or SpeechBrain or other open source libraries or people in the industry doing cool research on the topic to give some presentations. So every week we'll be having, every session. At the beginning it will be every week, then it will be every 2 weeks. There will be some related resources. So those could be papers, those could be blog posts, those could be YouTube videos. During each session, you can ask. So let me show you some of the resources. So if you're watching this in YouTube, which is the only place where you can be watching this, hey, here, in the description, you can already find a link to the forum. So the forum is the perfect place to ask questions. So there is this thread, which is ML for Audio Study Group. Again, the link is in the description for YouTube, and you can ask questions here. At the end of the short presentations, we'll go over these questions and we'll be answering them. The second one is the GitHub repo. So this is kind of a recopilation of all of the resources in a single place, including a schedule with which are the topics that we are going to see, which are the recommended resources, and later on we'll be adding like more supplementary resources. So right now we have some slides, we have some research papers, toolkits, and demos, but we'll be sharing more as this study group progresses. And finally, we also have a Discord. So this is the Discord. So if you're from Discord, hey everyone. And you can find a channel which is ML for Audio Study Group. And this will be the place between the different sessions in which you can come, you can do a bit more of an informal discussion or just brainstorm ideas or like ask like how to do certain things if you prefer to not post in the forum. But at least for the session of today, we are going to be focusing entirely in the questions asked in the forum. So please, if you have any questions in the next 30 minutes, in the next hour, feel free to come here and ask your questions here. Yeah, that's pretty much in terms of what are the expectations. Really, like this is a community-led effort, so feel free to make it whatever you want it to become. So if you want to focus in papers, if you want to focus in a certain areas, if you want to focus in music, for example, feel free to propose papers, to propose ideas, to discuss these kind of topics. So the timeline is that today we'll do like a kickoff session. We'll kick it off like very like easy, so it won't be like super complicated stuff. Next week we'll do like a automatic speech recognition. We'll explain in a minute what that is. and also like very basics of what audio is and what are the challenges in machine learning. And then in January, to kick off next year, we'll talk about TTS, that's text to speech. And after that, we'll decide as a group what papers we want to do, if we want to invite speakers, if we want to do like a deep dive into any specific task. Having said that, I think Bibi will continue the presentation.
Perfect. All right. My screen's visible, right?
Yeah, looks good.
Okay. All right, awesome. So, what we're gonna do for the next 20 to 25 minutes is essentially go over like the two broad applications that we come across within spoken language understanding within speech, right? One of them is speech recognition, and the other one is text to speech. And we'll essentially superficially understand what they are. Why is it that we should be, more cognizant of what's happening over there, and basically just get an intuition of what all is it that we will be sort of covering or tackling in the weeks to come. um, with that, this is like a very exciting time for spoken language processing in general, right? We now have very strong and like very capable speech recognizers in our phone, which is Siri, Google Assistant, Alexa. We have really nice um, text to speech models. Like for example, every time you go to Google Translate, you're able to write in English and then be able to get text, then be able to get speech out in Spanish or in German or whatever the language may be. And all of this is happening all because of neural networks. And we'll get to how this was done before, but right now pretty much all sorts of automatic speech recognition or text to speech is done using end-to-end neural networks. So everything that you see is basically a neural network, and in the weeks to come, we will sort of unpack this a bit more through papers or through sessions like these. Um, so let's first understand um, the overarching sort of field a bit more. So in general, what exactly is a dialogue, right? Like a dialogue is something which wherein I say something, right? So I say, hey, do you want to grab a dinner? Then someone says something like, sure. um, where do you want to grab a dinner? And then I understand that and I say, does the city center look nice to you, right? And so all this back and forth between me saying something and someone responding to it is basically a dialogue, right? And us humans are really nice at understanding dialogues. However, the machines are not. For a machine or for an algorithm to understand that, they need to have a lot more things in place than just you know just one model understanding everything, right? A simple example of this is when you ask Alexa about the weather. So you have to say, hey Alexa, what's the weather like today, right? And then Alexa would tell you, hey, it's snowing and it will continue to snow till 5 p.m., for example. But then if you ask anything else, you need to again say, hey Alexa, and then say the next thing. So there's no like dialogue or there's no conversation that's happening per se, right? And that's one of the limitations that we'll discuss later on as well, in the in the in the purest sense. um, but yeah, like there are certain design considerations that we have to take into consideration. So a thing like Alexa, wherein you can ask one thing to it at a time, works quite well because we typically have just single questions. What is this? Can you play that? Should I carry an umbrella? And so on and so forth, right? Then there can also be purely like translation based tasks, wherein like you say something in one language and you expect um, the model to return output in another language. It can be text, it can be speech, right? So all that we're trying to sort of portray over here is that there are like multiple design considerations that go into creating a conversational agent. A task which is as simple as just talking for us is very difficult um, um, for the machines, if I may call it. And an example of this is something that you see on the screen, right? So, say for example, let's take Mary here talking on the phone, and she is saying something um, which the phone perceives as waveforms, right? And then the phone performs something called automatic speech recognition, which takes the waveform and converts it into text, right? So now we have some natural language, right? And then this natural language um, goes into a spoken language understanding unit, which takes the text apart. So from leaving from downtown, which you see over here, we understand that okay, so she's leaving from downtown, right? And there is like some sort of a depart time, which is 1 p.m., and there is some sort of a arrive time which is 1 p.m. again, right? And there is some sort of a probability associated to all of this. um, then there is a dialogue state tracker which basically tracks all of this through time. So Mary would essentially be having a lot of conversations through and through, or like a lot of back and forth with whoever she's talking with. In this case it's a bot. And so we will keep a track of all that we've spoken with her in like a dialogue state tracker, right? And then we'll have certain policies. So um, she's saying, for example, leaving from downtown, then we can basically have some sort of a activity or some sort of an action to that. In this case, the dialogue policy chosen was to confirm whether it is downtown or not, right? And then this policy goes into the natural language generation part, which generates the text called from downtown. Is that right? And then that text is converted into speech, right? So this is again like all of these are individual components of an entire conversational agent. However, you have to realize that it's not just that a model understands the speech and it you know returns back some speech. It's much more complicated than that, and all of these have different levels of accuracies. Right now some work quite well, some don't work that well, some are end to end, and some are more rule based. For example, a policy in a more specific domain would almost always be um, rule based, and so on and so forth. So now that we've sort of covered like in like a broad overview of what is it that the overall sort of conversational setup entails, let's look at two key individual parts. So first we'll cover speech recognition, and then we'll go over to text to speech. Again, this is at like a 10,000 feet level, just to give you an intuition of what's happening. Um, so let's talk about speech recognition, right? Simplistically, let's assume like a very simple scenario wherein we just want to recognize two words, yes and no, right? Now, if we from our machine learning background, if we were to think of an example of recognizing yes and no, it's a very simple classification problem, right? You give it some sort of a waveform. You give your model some sort of a waveform, and then you um, expect the model to through different patterns understand which is a yes and which is a no, right? That's quite simple. However, in real life, it's much more complicated than that. We just in English alone, we have more than 64,000 words that we use um, more often than not, right? And then while while we talk about just the words, um, different speakers have different ways of talking about things. So, to give you an example, I'm from India. I have a certain accent when I speak in English. Similarly, someone who's from the UK will have certain accent while they're speaking, as opposed to someone who's from the US, right? So the accent, the pitch differs in general, right? Um, More specifically, the way I say one word differs from the way I say something continuously. And this is basically the procedure. We will get to that in the Q&A, because there's a question around that. But just to give you an example of this, if I was to just say Alex, just the word Alex, right now Alex is an isolated word, and the way I say it is much different than if I put it in a sentence. So if I put it in a sentence like, "Hey Alex, do you want to grab a beer?" or something like that, then like my emphasis on the word Alex is much less than when I just said it as an isolated word, right? Um, and so this is just to tell you the differences that we have in the speech itself, right? So there are a lot more factors than just converting a waveform um, to text when it comes to speech recognition. Um, but yeah, we'll get to how we solve that later on. Um, yeah, and this is the most simplest form of this is what like ASR is. Like you have some form of a ASR, sorry, some form of a waveform, and then you convert it to it's time for lunch. For example, in this case, this waveform actually corresponds to it's time for lunch. Um, and the way we do it, or like the most basic architecture that exists in the neural network world, is an encoder decoder um, setup. So you have the waveform, and then you extract features using a MEL spectrogram, and then you feed it into an encoder, and then like specific sequences, or like specific parts of this particular waveforms are then like converted into a character, and then all of those are pulled together to eventually give you a sentence, right? So there's like a lot more that goes into actually um, building these end-to-end models, but this is the most simplest setup that exists out there, right? And we will cover this specific architecture in more detail next week. But I just wanted for you all to get a sense of what exactly is happening, right? So essentially, this is a sequence to sequence task, right? So you have sequence, which is a waveform. You take that, you convert it into a MEL spectrogram, you pass it into an end-to-end model, and it gives you text at the end, right? One thing to note is that like waveforms are much more dense as compared to text. So for example, this is it's time for lunch. This is much more dense than just four tokens saying it's time for lunch, right? So we also like do some sort of subsampling and like some sort of feature selection as well in between in end-to-end models that happen automatically. But yeah, just wanted to emphasize more on this. So up until up until now, we've sort of understood what ASR is, right? So ASR is the task of taking a waveform and converting it into text, right? And we've understood like a very basic model um, which does this, right? A very simple encoder decoder approach which does this end to end. But how well have we done so far? So one of the um, most simplest metrics that we use within the ASR world are called is called word error rate. So what is a word error rate? So word error rate is basically the percentage of words that were misrecognized by the model. So if the waveform says it's time for lunch, but the model says it like it's time for dinner, for example. I mean, it will never happen, but let's take this example. Then there is one word which is wrong. So the most simplest word error rate, like the word error rate for this sentence would be 25%, because the model got one out of four tokens wrong, right? So you get like a 25% word error rate. Um, right now, if you see, like, especially for like English, we've reached a word error rate of 1.4%, which means that roughly like every one word of 100 words that the model transcribes would be wrong. In my opinion, that's like fantastic. Like, we humans make a lot of mistakes as well while we converse, and like, understand stuff as well, and we sometimes ask for, what did you mean by that, what did you mean by this, and so on and so forth. So I think 1.4% is quite nice in that retrospect. And there are like different data sets that are out there. So there's a switchboard data set, which is quite old, and it's basically conversation between strangers on the telephone. There's call home, there's social linguistic interviews, and so on and so forth. And you can see um, like the first one, which is Libra speech. It's the clean variant of it, which means that this was recorded in a studio. So like you had the perfect microphone quality, you had the perfect environment, and so on and so forth. You did not have someone banging on your door while you're trying to understand stuff, or you did not have like, a microphone like what I have on. Like, it's those were just pristine conditions. So of course, garbage in, garbage out. If your quality of data is great, then your model is great. But if your quality of input data is not that great, then yeah, the word error rate, as you can see down below, starts decreasing considerably. So especially for like Shime 5 dinner parties data set, wherein like the um, the audio was recorded from at a dinner party, but and also from distant microphones across the rooms. The word error rate is 81.3, which means like the model essentially almost always gets it wrong, right? So this is basically to sort of tell you that we do quite great when the conditions are pristine, but when it comes to real life scenarios, we're not there yet. Um, Similarly for Mandarin, over there we use character error rate as well, and like um, over there it's 6.7%. And I don't know if any one of you know Mandarin, but like Mandarin has like, just like in terms of prosodic features, has um has a very um difficult speech intonations when you actually speak it. So while us humans can understand it, for a model to understand those features in a very short time, that too with a very short corpus, or like very small corpus, is still a difficult task. um, so all of this was just to set the context of the fact that this is still not a solved problem. Like, so there are still quite a lot of things that can be done in the ASR setup to make it um, more beneficial for others. And one of the things which a lot of people in my research group work on is specifically about using different like creating systems for different languages as well. So, what about languages which have little to no data available? Like English has a lot of data, right? Similarly, for example, German has a lot of data. French has a lot of data. But what about some obscure language from India, for example, um, and so on? We don't have zero shot systems available. We don't have like few shot systems available for speech recognition. So in general, there's like a lot of things and that you can do when it comes to speech recognition, and more specifically when it comes to embedded speech recognition as well, like the ones that happen on your phone, and so on. So that was like, I hope you got a quick picture of what happens when we talk about speech recognition, and you got a quick sense of where we are when it comes to sort of speech recognition in general, and like what where exactly is it that the gap still exists, and yeah, we didn't talk about what we can do about it, but hopefully that's what we'll discuss in the times to come. Um, and So let's move over to speech synthesis now. So what is speech synthesis? Speech synthesis in its most simplistic form is to produce speech from a text, right? So if I give the text, "Hey, my name is Vaibhav," um, I get an output from the model which says, "Hey, my name is Vaibhav." So it converts text into speech, and as we saw from the example before, this is definitely used for in like personal assistants, so like Siri, Google Assistant, and Cortana, and so on and so forth. This can also be used for like announcements, so like the announcements that you probably hear at train stations can be used definitely for that. It can be used for like multitudes of other things also, like with the advent of deep fake and so on and so forth. You can sort of get different voice, so like voiceovers and so on and so forth, as well. But just in general, like the just the ability to be able to convert text into speech is text to speech. um, and The way this again works is again from like a end-to-end neural network approach. And like the basic idea is that you take some speech, um, which is in between say 5 to 50 hours. um, it's good if it's from one speaker, but again we have good multi-speaker models as well. Then you transcribe them, meaning you listen to the audio, and then you transcribe it into text, and then you feed it into um, an end-to-end model. Um, in the previous days, there was a lot more that you would do. So for example, you would understand what all phones does it have, which is like essentially mapping each and every character to like a phoneme using like an EPA chart and like whatnot. Now like with the end-to-end systems, you don't have to do that. You basically just give the um, the audio along with the transcriptions, and it works quite well in general. And text to speech is not like completely end to end. So like we first take we first take the text, and then we convert it into um, a Mel spectrogram, and then we take that Mel spectrogram and pass it into a vocoder, which converts it into speech. So there are like twofold steps that happen in text to speech. And The TTS part, the text to speech part, is typically this one, and this one, the second one is vocoder. So we have a couple of models for it, like HiFiGAN, Melgan, and so on and so forth. We will be at least talking about those briefly in the January 4th session, for sure. And like of course the pipeline to take text and convert it um, into Mel spectrogram as well. So this is actually a rather complex architecture, but I just wanted to sort of talk about the end-to-end part of text to speech. This is a Tacotron 2 um, model, which was from Google. I think this was released back in 2019 or 2018. And um, like what you can see over here is that there is like the input text, then you create a character embedding out of it, and then you have LSTMs, and then you have an attention between the encoder output and decoder, and then you have this one thing called stop token, which essentially predicts whether wherever you're at right now, whether it's okay to stop the sentence here or not. So if you're at if I want the model to create the Mel spectrogram of um, my name is Vaibhav, so at Vaibhav, it sort of checks whether it's good enough for me to stop right now and switch to a new sentence or not, right? And you can see over here that we get the MEL spectrogram over here, and then we have some form of a like vocoder. In this one they use wavenet, but effectively you can use any which converts the MEL spectrogram to the waveform. And as you would have realized by now that if you draw parallels from ASR, it's pretty much the same thing. It is also a sequence to sequence model, except just the other way around, right? In that one, you have a wave, and then you convert it into a MEL spectrogram, and then you feed it into the model, and then get text out. In this one, you do it the other way around. You have text, you create MEL spectrogram, and then you get the waveform out. Um, just a quick note over here. All of these like all of these slides were either taken from Stanford Speech Language Understanding course or from the um, uh, SLP book, and I've marked the link on the bottom right. So in case you're going through these slides later on, you can quickly just click on that and just understand the overall approach that I just explained in more detail as well. Um, there are like So with that, we can sort of finish the text to speech part. I think one of the things that I wanted to cover real quick over here is like how exactly do we measure the efficiency of a text to speech model. The answer is that like there's no right way to do that. Typically, a text to speech model is evaluated using a Moss survey. So like you get like a mean score. So like you take say 10, 20 test sentences, you pass it through the model, you get the corresponding waveform or the audio, and then you have say 40, 50 people listen to it and give it a rating on a scale of 0 to 5 as to how intelligible was it, how great was it, and so on and so forth. um, and um, then you get like a mean score, and then you sort of compare. But there's no like score like word error rate as such for text to speech, um, or at least none that I have come across so far. Let me put it that way. Um, yeah, and then there are like multiple applications um, in general. Like this is beyond text to speech, beyond ASR, just overall in terms of the applications of speech, right? There are like multiple of those. Like how can I extract information from speech, right? So how can I separate, say for example, there was a question in the forums about it. How can I separate like the singer singing from the acoustics, right? How can I separate that from the acoustics, and how can I like what can I do next with that? Can I understand the emotion of a person? Can I understand whether a particular thing is toxic or not? Can I identify a speaker in a room full of say 5 6 people? Can I identify who's speaking at this point of time, right? um, and can I, more from like an end-to-end dialogue system based approach, can I make reservations um, by talking to a bot? I think Google had a really nice demo for it a couple years back, wherein like they basically have two bots talking to each other and make a reservation. And what was great about it was that the models actually understood um, the the conversation so well that they also added like some um, prosthetic features in the speech itself, which was adding filler words like but does this work, and so on and so forth. And I think that was pretty cool. We're not there yet, but who knows, maybe in a year or two we're there. um, then we get to the last slide, which is what other speech related tasks are there. Like we spent a lot of time understanding speech recognition and text to speech, and that's because those are the two sort of most heavily time consuming tasks out there that we typically come across, and are an active research area. um, but there are like certain other tasks as well. For example, the most simplest one that I could think of was like wake word, right? How do you, like, when I say something, how do I identify when am I saying um, a short phrase or a word which lets my Alexa know that I am asking something to her, right? So or to it. Then there is, speaker diarization, which is understanding or like determining who spoke when, right? In a multi-speaker audio recording. Then there's speaker recognition, which is just identifying who the speaker is. So if I'm saying, and if Omar is saying something, then just segregating when is VB talking and when is Omar talking, and so on and so forth. Then there's language identification. This is used in like translation systems a lot, especially like end-to-end translation systems. Just understanding which language is someone talking in, or like identifying that, and then like using that information as a metadata to the to the translation model, and then um, passing that information further. Um, so with that, I hope you got like a quick sense of what these tasks are, what they can do, and how they sort of work. I wanted to quickly jump in um, and show you like a quick demo. Do we have time for that, Omar, or do we want to take?
No,
Do we,
yeah, go
okay,
ahead. We have
all
time.
right. So let me just quickly. Oh my God, it's the wrong one. I hope this opens soon. Uh, uh, yeah, sorry, my laptop's acting up a bit. Let me just search this. Okay. So on the GitHub repo itself, I put in like three Hugging Face spaces. I think let's quickly see one text to speech example and then like one ASR example. So just a quick refresher. Text to speech is something wherein we take an input text and create some sort of speech out of it. So let's say, hey, I am part of a HF, and then we hit submit. Um, One thing, like while this runs, and you will observe right now, is that typically these models are there is like it took 5 seconds for the model to create this speech, but 5 seconds is also too much, specifically when it comes to a lot of dialogue based systems. So there's also another active area of research on like how to reduce this inference time as well. Yeah, I don't know if you can hear it. Were you able to hear it?
No, no, but I think it's okay.
Yeah.
I would suggest people to just I put the link in the comments, so feel free
Oh,
to try out the demos directly yourself.
yeah, perfect. And I just wanted to give a quick example of why we need better text-to-speech systems over here with this example. If you actually just type this in the space and just hear the audio, you'll see that the model messes up big time at HF demo, just because it does not know whether it's supposed to pronounce this as HF or as huff, like the sound HF, you know, and it basically does something in between in the output audio. So there's still a lot more for us to do when it comes to creating good text-to-speech systems. Let's take another quick example of ASR, and then we can head to questions. Um, I am not going to record anything. Oh, wait, where are the demo files? Huh, weird. Um, I don't know why the demo files are not showing up here anymore. Maybe this got updated from yesterday. But you can basically try this with your own mic. Just hit record and see what the wait. This is speech translation. Maybe I linked the wrong repo here. But what this one? Oh right, I linked the wrong one. But this one, what this does is that you give it speech in one language. Say for example English, sorry, like say I say something in English, then it performs like language identification, and then whatever language I give it, for example, Swedish, it will convert that and um, pass me the translation of it in the speech form as well as in the written form. So do check this out. I will link the ASR demo in the repo and post it on the forums as well later on. But yeah, just wanted for you to have two points of things that you can just try out what we just spoke of just right now. So yeah, with that, I will stop sharing.
Awesome. Cool. Yeah, so we'll go to the questions in a minute, but just as a quick overview of what will be happening, probably like some of the technical concepts that BB mentioned, maybe you don't know them. For example, spectrogram. I think that's like a good example. So we'll go a bit more in detail on what it really is. I think the idea of this initial session was just to give like a high level overview of the field. But then next week we'll do an intro to audio. So what's a sample rate, what's a spectrogram, and how the data is processed for machine learning. And then we'll do a deep dive into how automatic speech recognition is. Having said that, I think we can go to the questions. So the first question, which was by me, it was more to kick things off, and I think Bibi already answered quite well in his presentation. Let me criticize. Is what other kind of tasks can be solved in the auto domain? But I think this was solved very well. Okay, so let's go first with this one from Amitness. Are there any works that directly perform modeling on raw audio signals itself without using text as an intermediate medium? How common is it compared to doing automatic speech recognition and then running regular NLP models on text?
Right. So it's actually much more common now, especially from like 2019 onward. And I'll just um, link to this um, to this paper from Google. I think this was back from this is back from 2019, and there's this blog that they posted about translatron. It's a bit of a mouthful, but they basically take speech and directly convert speech into speech in the target language, right? So they take speech in one language and convert it into speech in another language. Just in general, speech is much more rich, right? There is like this whole concept of prosody which comes into speech, which is if say I'm saying something. Let's take for example a question answer thing, right? So if say I say, hey, who ate my cake, right? So hey had a slightly higher pitch intonation, and then there can be a response to it saying, Mary ate your cake, which is a informational focus, and there's like a normal response to it. But what if this was something like, no, um, John ate your cake, right? So there is more emphasis on John, and there is more like there's a higher pitch in no. So just that, just from like a waveform standpoint, just from the way we speak, there's so much more richness that is available as opposed to just like a one-dimensional text vector out there. That it makes more sense to do stuff on speech. It's now with the advent of as much like practically infinite compute out there, it's much more easy to build your model straight from speech. So my answer would be yes. And I can once I respond to this on the forums, I can also link a couple of papers that will help you understand that better.
Awesome,
uh,
thanks a lot. There was another question which is unrelated to this one, which is if it's possible to build a model or to solve this task of counting filler words such as and that kind of words. And how
yeah,
would you model this? Yeah, go ahead.
I think there are like multiple ways to do that, and I think the most simplest one that I could think of doing that was, um, like, first let's think of this as the most let's think of this as a classification task, right? So your speech signal let's assume that you have 10 milliseconds of windows of your speech signal, which you input to your model, and then the model gives you some sort of character. If you go back to the ASR domain, right? And like assume that all filler words have like certain disfluency associated to them, right? So say for example, if I'm saying something, let's take an example of I am going to the cafe and I'm going to offer and I'm going to order a cappuccino. Let's take this sentence as an example. So if I was to say it fluently, I would say I'm going to go to the cafe and I'm going to offer I'm going to order an espresso, for example. But if I was to put some filler words, it would be I'm going to the cafe and I am going to order um, an espresso. So you can see that there were disjoints in the entire speech, right? So one of the most simplest ways to just like look for these disjoints in the speech, right? And then you sort of take those disjoints and you just like classify a model on it, right? So then it becomes like a very simple, like from a mel spectrogram of the speech, you basically just search for whether or not that disjoint is there in the spectrogram itself, right? And I think you basically just need to like in terms of learning what to do with that, you just basically need to learn um, how to convert mel spectro like how to take features from mel spectrogram and just um, create a very small data set. Again, like you can create it yourself, or you can just use one of those conversational data sets that we were talking about. They have a lot of filler words. Just take 1 or 2 hours of recordings, transcribe it, um, because in your case you just have to transcribe whether there is a filler word in this particular window or not. So it's a yes or no thing. It's not as complicated as knowing everything out there, and you can do it that way. There's actually a very interesting paper that Omar and I were discussing this morning. Let me see if I can find the link to it. Um, it is this one. So I'm just sending it to Omar once more so that he can put it up. And yeah, if if it's there's like an entire like part of like um, how they identify filler words in this. And if we just like zoom in a little bit more on the figure one on the right side, yeah, so like you first do like a filler word segmentation, right? And then you identify where they are, and they use the same disfluency to do it. And then you can basically replace them with static noise and so on and so forth. In your case, once you identify that, you can increase the count of filler words. So this might help. Um, Again, there are like multiple ways to solve it. This was the most simplest one that I could think of.
Awesome. Thanks a lot. Quick pause. There was one question from YouTube just to answer that one. The question from Ali is, what is the SLP resource again?
It's
And
the
just to answer from the GitHub repository, it's a speech and language processing. It's actually a super nice book. It's like for speech and language processing, but it really is like a super nice introduction also to a lot of NLP related stuff. And we recommend specifically the chapter 26, which you can see here at the bottom. So it's for ASR and TTS. And this one, part of it is actually one of the recommended resources for the next session, the sections 26.1 to 26.5. Awesome. Again, remember that we'll try to prioritize questions that are in the forum, so please feel free to ask questions here. Yeah, so there's this question from Sharma. Is out of curiosity, is it possible to separate words and music from a song audio?
um first of all, I want to say like thank you so much for asking that, because I found a new technique while I was researching the um, answer to it, and I'm just sending the link over for that. You can effectively, like if you have um, enough speech or like enough music in your context, then you can run something like an PCA or like some sort of a decomposition, right? So it can be an SVD. In the case of the In the case of the paper that you see over here, they used RPCA, which is like a modified principal component analysis, and they use that to separate the acoustics from the from what the speaker was actually saying. But in general, this becomes like more of a separation task, and this is very much doable provided you have enough data for it. I think one thing that you will have to take into consideration is when you're building something like this, you will need to have the same domain of data. So, say for example, if you're dealing with um, country music, then the way you would separate country music would be much different than, say for example, heavy metal, right? Just because of like separate acoustics out there. We will
Awesome,
be
thanks.
sharing these resources later on. Yeah.
Yeah, everything will be in Discord and also in the forum. We'll be sharing all of this. And also, like again, if you want to further discuss this like in more detail, rather than a question answering format, more or less a discussion, feel free to use Discord to do that as well. Okay, we have only 2 minutes. We have 3 questions more, so let's try to briefly answer these ones. So this one from Alexei Dorkin is a significant portion of information is lost when we transform speech to text. There's tempo, timbre, volume, etc. All these aspects may be helpful on downstream tasks, as it would seem. And for example, if we want to determine emotion being expressed, things like pitch, volume, and tempo can be useful than the content itself. So, for example, considering utilizing may instead of meaning in my previous sentence, I think it makes sense to consider using non-verbal information for ASR, automatic speech understanding and generation. And the question is that a thing?
Yes, this is the thing, and like if you were to ask this, say in 2017, then this was not a thing. We were still converting everything to text and doing stuff like that. But like now, this is very much a thing. You can actually look for an example like this with Siri. At least I've tried this. If you talk to Siri in a elevated pitch, with like an angry um, voice, then the Siri's response would be actually like really mellowed out. Like the pitch with which like it she would, or like I don't know which gender you would be using, but like whichever one you're using would be quite mellowed out. And if you ask it with like a happy way, like the overall pitch with which it responds actually changes a lot. And I think that's a fantastic example of all that you're saying, and um, you know seeing that in real life.
Awesome, thanks. Uh, I think we'll skip this one because it's like super specific to the reading, if that's okay, and we will answer directly in the forum. I think that might work better.
Yeah.
And the next question is there a code app available where we can try speech recognition on beginner intermediate level? We don't have one right now, but I think the idea will be for the next session to have one of these.
Yeah.
Yeah, so we'll update on that.
So yeah, there will definitely be one in the next session for sure, wherein you can just quickly take a um, Hugging Face model or a speech brain model and just try it out. Yeah.
Awesome. Yeah,
So
in case, just to share a couple of quick resources, maybe. Like if you want to go to the Hugging Face website, if you've never done it, you can go to models here at the top. And then you can go at the left, click this plus 12. And then you can select all of the different audio tasks. So here, for example, you can search for automatic speech recognition, and you will see that on the code we have like 800 ASR models. And you can even click here, and we have like widgets here. This one is Wave to Back 2 from Facebook, and you can try it directly here. So we'll show you how to use this in Python. It's like very easy to use, both from an API perspective and from a library perspective. You can try both. And this is using the Transformers library, but we also have integrations with other ones. So for example, if you don't know SpeechBrain is like a very nice library for different audio related stuff. So for example, they have a audio source, this is a speech enhancement model. So that removes noise, but there's also like audio source separation models and other models that you can also try it directly in the browser. So that's very nice. And this library is SpeechBrain, in case you didn't know it. Okay, so I think we have one last question. 1 second. Yeah. So the question is, if the model generates longer transcription than ground truth and every word is wrong, would the word error rate be greater than 100%? And I think the answer is yes. Maybe let's show you the formula for word error rate. So this is Wikipedia, which is a great source. So here, the n, the number you divide, is the number of words in the reference. So that's like ground truth, right? So on the top, you might end up having like if there were only 10 words and at the end you generated like 10,000 words in the transcription, the word error rate would be much higher than 100%. Is that right, Vivi?
Yeah.
Yes, right?
Yeah.
Awesome. Yeah, so there's this question, which framework of speech recognition gives pre-trained model that we can do fine-tuning easily for domain adaptation?
Yeah, I think, I mean, you can pretty much use any speech brain models for it. They have plenty models available for ASR, and you should be able to just fine-tune those. So I think maybe if it makes sense, then I can go through the tutorials, and there is one which does this, and I can probably link it in the forums again. Um, so you so you will know that. But just to answer speech brain.
Yes, that's good. Okay, let's answer this last question, and then I think we will finish this session. Is what's the state of the art for speaker recognition?
I don't remember that actually, but I will get back to you on this. It's much higher than you think. It is like and there are, at least I remember, there are some models which I saw in a paper last week. I will look through that, and I will find it. But if I'm not completely wrong, SpeechBrain should have something
Yeah, yeah.
like this as well.
SpeechBrain has like this speech classification problems,
Yeah,
and there it has like a speaker identification models. I don't know if it's the state of the art, to be honest. The models are also on the hub, so you can also like search here. I think it's this one. Yeah, speaker verification. There must be another one for this, but I think this should work, and this one that you can already use. But yeah, I don't know what's the state of the art. One resource that might be useful, but I don't know what's the dataset normally used for this specific task. But you can search in papers with code datasets. And for
right,
example, for ASR, we use libre speech, right? So you
right,
can always click here, click the dataset, click the benchmark, and there you will see a comparison of different models of the speech 2 and like different architectures. And you can even like click it and find which are the papers and which are the results presented by these papers. For example, here conformer plus wave to peg 2 plus speak augmented based noisy student training with library light. That's long, but yeah, anyways, the metric value was 1.4 word error rate. So this is a good resource if you're interested in one specific task. It might be easy to search here as well. Awesome. I don't think we have any other questions. Feel free to join Discord. If you don't know where Discord is, the link is right in the video description. You can also come here. There's the ML for audio study group. Here is the full name at the top. Feel free to join. Feel free to ask any questions. See you next week. Just as a quick reminder, there are like 2 recommended resources for next week. The first one is from FastAI. This is a Colab, a Jupyter notebook that gives a very like introduction to the topic. It's very basic. There might be some like very technical concepts. Don't focus too much in those. The idea is to get a high level understanding of it. It's not to become an expert in speech processing, in speech signal processing, but just to get a better understanding on what's the data we are working with. And yeah, the second resource is the book, as we were sharing before. That's this chapter 26. This is all free. This is everything's open. And yeah, ideally, try to read these two resources beforehand. Try to post any questions you have directly. We'll open a new topic later today, so you will be able to ask questions there. And just as today, we'll spend like 20 minutes answering some of those.
Yep.
Having said that, thanks, Vivi, for the awesome presentation. Thank you, everyone that joined. There will be the video in YouTube. The presentation will also be shared, unless
It's
it's
already
already,
on.
it's already
Yep.
on. Oh yeah,
Yeah,
it's
in the
slides
slides.
here. Awesome. So you can find the presentation here as well. Uh, yeah, and once again, thank you, everyone.
All right. Bye bye.